Alright guys, so let's take a look at how to look at a parallel circuit. So this is a parallel circuit, and it gets its name because it's got an abundance of parallel lines. But it's also got a lot of nice, cool features. Now, the first thing you'll realize, guys, is you should say, "Wow, there's a lot of current routes." So our current leaves right here, and then it goes here. But then it gets to this junction, and then some of it's going to go this way, and some of it's going to go that way. And the interesting thing is that once again, from this point, if I think about it, if I go right here and I go, okay, so here's a point, let's call it A, and I'm going to go over here to point B. Well, there's only one route to go from A to B, so that means the current has to be the same through that one route. So that means that when I get over here, that this current right here, these are the same. And then this from here to here, that's the same current too, guys. From if you look at it from this point to this point, this current, whatever goes through here, it's all the same. So, and then these two that split up before come back to form the original current. And you may be saying, okay, Mr. John, give me some numbers. I'm a little confused. So let's do that. Let's just speak in arbitrary numbers. So let's say we leave the battery and we've got 10 amps of current. And then let's say we reach this junction, and let's say 8 amps go this way and 2 amps go this way. And then it's going to pass through. It stays to go from A to B. There's only one path for it to go. So when it gets over to this other side, it's still at 2 amps. From here to here, there's only one path, so it's still 8 amps. So when we get over here, they actually recombine to form the original 10 amps that travel back into our battery. And I think that's pretty interesting. Um, but we'll see some other features as well. So that's the important thing about the current, guys. The current's going to split up, but then recombine later. And that does offer some interesting dynamics. Let's see, though, what happens to our voltage, because our voltage does some silly stuff too. So our voltage, it leaves the battery over here with 3 volts, and it should go all the way here. But when it gets to here, it's kind of confused. It may be a little confusing. Just even think about it. The voltage is not confused. The voltage knows what to do. So let's say this is point A. The voltage gets to point A, and it really doesn't know what to do. It can go either way. But here's the thing. When it gets over here, well, what's the voltage right there? Well, if you think about it, is there anything from here between these two red dots? No. So the voltage just has to be the same between our two red dots. And what does that mean? Well, that means that this point is right next to our battery. It's 0 volts. And this point right here, it's 0 volts. So, okay. Well, when we go from point A to this new point, obviously call it point B, we have to go from we can either go this way or we can go this way. But the important thing is this. Either way you go from having 3 volts to 0 volts. So V2, the voltage lost to resistor 2, is 3 volts. And the voltage lost to resistor 1, V1, that's 3 volts. So that's very, very interesting. So both these are going to have different voltages lost. Or the same voltage lost. Blah. I didn't even say anything that makes any sense. And we can actually use these to calculate the current. Because remember last time we talked about this, we said Ohm's law V1 equals I1 R1. And I'm going to simply just go 3 volts equals I1 and then 5 ohms. And now I can just find out that the current through I1, this current right here that I was just talking about a second ago, I1 is 3/5 of an amp. I'm going to leave that off because for some reason I'm drawing really poorly here. But then also when we get over here, we know that this is 3 volts. And when I do that, when I'm looking at resistor 2, it's V2 equals I2 R2. And I have 3 volts because it's got to go from here, 3 volts to 0 when it passes through this, when it goes this route right here. And I don't know the current, but I know the resistor, it's 9. 9 ohms. So I'm going to go 3 divided by 9, that's 1/3. And it's 1/3 amps equals I2. And then you can say, okay, well, remember when I did this a second ago, remember the current came in and it split up at this point. It split. One part of our current went this way, part of our current went that way. Well, remember, guys, the current that goes into a junction has to equal the current that comes out of a junction. So if these two values, oops, if these two values come out, this 1 and this 2, what must go in must be the addition of these two. So it's 1/3 plus 3/5, which is going to be something like 9, 5, like 14 fifteenths. That doesn't seem to be right. But something interesting. I think that is right now whatever. I'm too tired. Yeah, 14 15 seems about right. That's going to be our current coming out of our battery. How do I know that? I go 1/3 plus 3/5, leaving my units off, but they're amps. And find the common denominator. 1/3 out of 15 is going to be 5/15. I don't know why the top by 5 is not working. Plus 9/15 equals 14/15. And there we go. We've got our answer for our current through our battery. We've got everything. It sounds like a great time. All right, guys. Talk